In section 6.6, we're going to look at the integration by substitution technique of solving an indefinite or definite integral. This is an important technique that we are going to be using throughout the rest of the semester. So we have already looked at a few rules of antiderivatives that have gone backwards through some basic derivative rules, such as the reverse power rule, and then some straightforward applications, such as the rules for sine and cosine. Integration by substitution, however, is going to go backwards through a technique of the chain rule. So that's one of our big derivative rules. And in our next section, integration by parts, we're going to look at the product rule instead. So in order to understand substitution, we should first look at the chain rule of derivatives. So let's review the chain rule. The chain rule says that the derivative of function composition, f of g of x, is going to be equal to f prime of g of x times g prime of x. We are going to call f the outside function and g the inside function, having g inside of f as the function composition. We talked about in the derivative review section about how we can break down the chain rule into 3 steps. And we're going to think about these 3 steps as we go through the technique of substitution. So one is we take the derivative of the outside function. That is, we're going to do this f prime of the outside function. But inside of that, we are going to leave the function alone. We're going to leave the inside function alone. We're going to continue to have g of x just as we did at the beginning. And then finally, we are going to multiply by the derivative of the inside function, this g prime of x. When going through a few examples, we're going to show that we're actually going to be going backwards through each of these 3 steps. So to think about substitution, we need to have function composition. We need to have an inside and outside function. And we also need the derivative of the inside function elsewhere in the integrand. It needs to show up in that function that we're taking care of. So in this first example, we have the integral of f prime g of x times g prime of x. This is the right-hand side of the chain rule. If we go backwards through that, we're saying that the antiderivative of that function is f of g of x. Again, this is the opposite of saying the chain rule. The derivative of the right-hand side is equal to the left-hand side without the integral. So let's look at a few examples that are in this form where we see a function composition, and then we see the derivative of the inside function elsewhere in the integrand. So in our first example, cosine of x squared times 2x, in this case, we're saying that the f prime here is going to be this cosine. We're saying the g of x is going to be this x squared, and the g prime is the 2x. And this works out because, again, 2x is the derivative of x squared. It's the derivative of the inside function. So if this is the case, we're saying that f prime is cosine of x. And our final answer should be f of g of x. So we need to figure out what is f here. That's just going to be the antiderivative of cosine, which we know is going to be positive sine of x. So our final answer here should be f, which is sine. We're going to leave the inside function alone. That just be x squared and then a plus c. Let's try that again. Let's do e to the sine of x times cosine. In this case, the outside function is e. That's going to be our f prime. The inside function is sine, and the derivative of sine is cosine. And since that cosine is the derivative, this substitution, this backwards of the chain rule is going to work. What we really need to do is take the antiderivative of the outside function, this e to the x. That'll be just e to the x, and our final answer should be e to the sine of x plus c. One more time, we have this outside function here is going to be 1 over x. It's kind of this like whole thing in parentheses. The inside function is just the denominator, x squared plus 3x plus 1, and the derivative of that is 2x plus 3. So again, what we need to do is think about what is the antiderivative of 1 over x, and in that case, that's natural log of absolute value of x. But we're going to leave the inside function alone, x squared plus 3x plus 1 plus c. Now, all of these examples we are not going to do in this form. This is just showing this basic idea of inside-outside function and that the derivative of the inside needs to be somewhere else in the problem. We're going to have this technique of substitution. We're going to have a step-by-step method in order to solve problems like this. So let's go through some of these steps and note that the problems that we had on the previous page were easy because there weren't extra constants and it was given to you in the form that is easiest to identify those functions. So here are steps that we're going to reference through a few examples. Step 1, we're going to do the actual substitution, and that is we are going to replace the inside function with u. Our choice of u is arbitrary. We could choose any letter. It's just common practice to let u be this substitution. And we're going to make sure that the derivative of the inside function is elsewhere in the integrand. Otherwise, this technique is not going to work. Step 2, we're going to take the derivative of u. There's something important about the derivative of the inside function, and we're going to represent that as du dx, the derivative of u. Let's recall this notation. The derivative of u we can think about as d dx of u, and what we're really doing is just taking that u and putting it in the numerator, and we have a du dx. Why we're doing that is so that we can replace the dx in the integral. So we need to replace dx in the integral. So we're going to write that equation with dx equals. Step 3, we're going to rewrite the integral in terms of u only, making sure that all x's are canceled out. And this is a good step that if we know that after cancellation there are both u and x in the integral, then we've made a mistake. We should stop and try to figure out the mistake. And the mistake may be that substitution doesn't work for this integral. And note that if this is a definite integral, we are also going to rewrite the bounds in terms of u as well. Everything in the integral has to be in terms of our new variable u. Step 4 and step 5 are the easy parts of this problem, and that is we now get to take a straightforward antiderivative in terms of u, and then we're going to put the answer back in terms of x. Or if it's a definite integral, we're going to leave things in terms of u and evaluate the bounds. And we'll see why we're going to do that in an example later on. So now let's look at an example, and we'll go through it very carefully, step by step. So the first example here is find the integral of 3x cosine of x squared dx using substitution. And note that this is very similar to our first example that we had a couple pages ago of cosine of x squared times 2x dx. In that case, 2x was the derivative of x squared, and we were able to see what the answer was at that point. This is a little more complicated, and we're going to see what happens here. So the first thing we have to do is identify what is the inside function and hopefully what is the outside function. The inside function here is going to be the x squared. That x squared is inside of this cosine function. We're going to write that as cosine of parentheses, or maybe you could say cosine of x. Either way is fine. And I know that this is going to be a good choice of the inside function because the derivative of the inside function is somewhere else in the problem. So the derivative of the inside, which is 2x, is also in the integrand. we're just going to say differing by a constant. So it doesn't have to be exactly 2x, but it's the x that is important there. That's somewhere else in the problem. That 3x there. So our first step really is very simple. It is just saying we're going to let u be our inside function. U is equal to x squared. Step 2, we're going to take the derivative of u, and the reason we're going to do that is because I need to replace dx in the integral. So again, what we're doing is we're going to take the derivative of u. What that means is I'm going to take the derivative of x squared. That's going to be 2x. But to make this easier, we're just going to say, instead, let's do the derivative of u with respect to x, du dx, is going to be equal to 2x. We can just write that down in just that form. And having it in this form allows us to do some algebra with the dx and du. So at this point, we are going to solve for dx in this equation. So the first thing we should do is maybe multiply by dx on both sides. So we do that, we're going to have du equal to 2x times dx. And if I want to solve for dx, then I'm going to now divide by 2x on both sides, and that's going to give me du over 2x is equal to dx. And that's what I want to do in this step. I want to find the derivative, and I'm going to solve for dx. In the next step, we're going to bring everything together. So we're going to rewrite the integral in terms of u only, making sure that all x's are canceled out. So let's remember what our initial integral was. We had the integral of 3x cosine of x squared dx. And we know that this x squared we can rewrite as u. And we know that the dx I can rewrite as du over 2x. So rewriting that in terms of u now, I have 3x cosine of u times the derivative of u, or du, over 2x. And what I say is that if after cancellation there are both u and x in the integral, there's a mistake. But note that there is some cancellation I can do. There's an x in the numerator here and an x in the denominator. And I can cancel those out, and I will be left with 3 cosine of u du over 2. Then I can simplify this integral a little bit. I have a constant of a 3 in the numerator and a 2 in the denominator. So I can bring out a 3 halves constant cosine of u du. Or again, I can write that as 3 halves on the outside of the integral cosine of u du. And what I've done at this step is I have now translated this integral, which usually had x, and now I've translated it in terms of u. And the reason I did that is because now this integral is easy to do. It's a straightforward antiderivative. It's one of the rules that we wrote down in our antiderivative review section. We just have a rule for it. There's no thinking that we have to do. So step 4 says we're actually going to take that antiderivative now. We have 3 halves integral of cosine of u du is going to be equal to 3/2 sine of u plus our constant c. And that is basically our answer, except that since our problem was given in terms of x, we should have our answer in terms of x as well. So there's one last step here, and that is we should write our answer as 3/2 sine of x squared plus c, rewriting the u as x squared. We can always double check our antiderivatives by taking the derivative of our answer and hope that we get our original function back. So if I did the derivative of 3/2 sine of x squared, the derivative rule that I would have to use is the chain rule. That should not be a surprise here because that we're going backwards through that rule with substitution. But this derivative would be 3/2, just comes along for the ride. We take the derivative of the outside function, that's going to be cosine. We're going to leave the inside function alone, x squared, and we're going to multiply by the derivative of the inside, 2x. And we see that there are some 2's that cancel out, and we can rewrite this as 3x cosine of x squared, which was our original function in our integrand. If we think about our steps of the chain rule, we said there's 3 things we're going to do. We're going to take the derivative of the outside function, and the opposite of that is taking the antiderivative of the outside function. And note that at this step right here, in step 4, we take the antiderivative of the outside function cosine of u. The opposite of leaving the inside function alone, we're just going to say is leaving the inside function alone. Nothing really to do there. But then also we say we have to multiply by the derivative of the inside. And the opposite of that is dividing by the derivative of the inside function. And we do that with this du over 2x. We're dividing by that derivative. Those are maybe some checks that you can do to see if you're doing the right thing in these steps. The biggest check that you have to do is, do you actually get rid of all the x's in your integral? Can you translate that integral only in terms of u, or are there x's left over? Now let's go through an example with a definite integral, and we'll see the little bit of differences when we have to deal with a definite integral. So here we have the integral from 0 to 1 of x squared over x cubed plus 5 dx. And maybe the most complicated part of these problems is correctly identifying what is the inside function and what is the outside function. In this problem, it's not as clear what the function composition actually is. It is going to be the case that the inside function is this x cubed plus 5. One of the reasons there's a hint that that is the inside function is because the derivative of that is 3x squared, and there is an x squared in the problem as well. That's a good check that something good is happening here. What function is x cubed plus 5 inside of? That is going to be inside of 1 over something, or we can write that as 1 over x. So at this point, we should already have some checks. Maybe we should finish this step real quick. Here we know that u is going to be our inside function, x cubed plus 5. There's a few things that we know are going to happen in this problem. We know that we are going to divide by the derivative of the inside function. At some point, we're going to divide by 3x squared. So at some point, and in step 2, that's going to happen. We should be dividing by the derivative of the inside. That is the 3x squared. And we also know that at some point we should be taking this is going to be in step 4. We should take the antiderivative of the outside function. That's going to be the antiderivative of 1 over x. Not 1 over x necessarily, but 1 over something, maybe 1 over u, du, and that's going to give us a natural log of absolute value of u. That should be somewhere in this problem, and it's going to happen in step 4. Those are some checks that you can do that you should always have happen in these substitution problems. All right, back to the problem at hand. That's all just helping us out here. We know that right now u is equal to the inside function. Let's see if this actually works. We need to take the derivative of u with respect to x. That's du dx. So we already did that. That's going to give us our 3x squared. And when we're solving for dx here, we're going to multiply by dx on both sides. So that's going to give us a du equals 3x squared dx. And then we're going to divide by the derivative of the inside. (3x squared). And we get du over 3x squared is equal to dx. Now let's run through the last 3 steps here. Step 3, we're going to rewrite the integral in terms of u only. So let's do that here. We know our integral is the integral from 0 to 1 of x squared over x cubed plus 5 dx. But we know that this x cubed plus 5 is going to be our u, and we know this dx is going to be our du over 3x squared. So writing this all out, we have, this is going to be the integral from 0 to 1 of x squared over u times du over 3x squared. And if we do things correctly, these x squareds should cancel out, and they do, and we are left with a integral from 0 to 1 over u times du over 3. And note that that du over 3 is the same thing as a 1/3 times du. And we're just going to bring that 1/3 out in front. Now the only problem left here is that these bounds on the integral are in terms of x. So these bounds here are in terms of x, and we need to have everything in terms of u. So this is like x equals 0 and x equals 1. So we need to rewrite the bounds in terms of u. And the way that we can do that is by just using our formula that u is equal to x cubed plus 5. So in that case, if I have x is equal to 0, I know that u is going to be equal to, plug in 0 to that formula, I have u is equal to 5. And the other bound, x is equal to 1, plug that into our formula, and I get u is equal to 1 cubed plus 5, which is u is equal to 6. So I know that the actual integral that I have here is the 1/3 1 over u du, but in terms of u, this is the integral from 5 to 6. U is equal to 5, u is equal to 6. And since we want everything in terms of u, we need that. Now at this point, we have our straightforward antiderivative that we need to take. That's going to be this natural log of u. So let's take care of that. We already said we should have that at some point. We have 1/3 integral from 5 to 6, 1 over u du. That's going to give us a 1/3 natural log of absolute value of u evaluated from 5 to 6. And those are u values that we're evaluating. And now we've taken the antiderivative. That's that. Note that these are u values, so we can just plug those in at this point to the definite integral, and that's our last step here. This is going to be the same thing as 1/3 natural log of absolute value of 6 minus 1/3 natural log of absolute value of 5. And I want to make a note that what we could have done also is we could rewrite everything in terms of x and evaluated it from 0 to 1, noting that these are now x values, and plugged those in and got the same answer. Using the fundamental theorem of calculus. But that's just going through some extra work, and we don't need to put everything back in terms of x because we've already changed the bounds in terms of u. So that's another way that we could do it, but it's just more work. So we're going to just rewrite everything in terms of u, leave it in terms of u as we do the definite integral. We'll look at some practice in the next video, going through some more substitution, looking at some different things that we're going to encounter.